And okay, it really is a beautiful case. And I will, if you want to get extra point in the paper, write the stuff that they are not in the chapter, and I'm going to talk about them. So take a note, take some notes as I speak, because this chapter, after all, it's introductory book, and the evolution of specifically this assignment or this kind of how to guess, when somebody writes numbers by hand and you give it to the computer and you ask him what numbers it is. So the zeros might be a little easy, but all those ones are very different. Very soon, very fast, you can get confused between 2 and any other number. Like this 5 can be almost anything. Somebody can think even it's 1, A different, this one, for example, it doesn't really look like a 6. This one might look like a 9 even, or this one definitely, this 4 could look like a 9. Yet, can you write a machine learning algorithm so you can identify those numbers? So stage number 1, which I think it's extremely, honestly, it's from conceptual way, it's broadening your way of thinking. If you take something, it's not really the technical part we're going to go over, and some of them I will skip intentionally because I don't want to be technical, but at least get the idea. And then I will talk about a different algorithm, or the idea of the algorithm that it's not in this chapter, which in real life people are doing those days, okay? So how was the approach in to try to solve this issue? I get an image, many images of zeros, many images of ones, etc. And in fact, in a database that comes with scikit-learn, there are already a database with a lot of images like these. There are about, if I recall well, it's about 70, if I'm not wrong, 70,000 images. What does it mean, a database of 70,000 images? So let me describe that first in Excel. And this is really good for you to understand, because it will go with you for a lot of things. If you go into this field, definitely. How do I take a picture like this one? Let's take the 5. I take this 5, okay? How would I represent it, okay? So first of all, it is an image. I mentioned last time that an image is a collection of pixels. You see, this is like a pixel. You see this little square? This is a pixel. This is a pixel. And those are also several pixels next to each other. Those ones are darker. Those ones are lighter. They are more gray. This one very closer to white. This one is definitely white. So you can say, well, if I take a little square around the 5, I can describe this 5 as a collection of little squares. And each square, it is a pixel. So if I have a picture of 28 by 28, you can think about it as if I have an Excel spreadsheet on 28 by 28. That means from here to here. And I have to move. You know what? Let's write numbers. 1, 2, 3, 4, 5, 6, 7. Let me drag it. It should be nice to me. And take it to 28. Fair enough? So I have 28 columns. And let me just add another row here. And I will write the numbers here from 1 to 28. Now, normal pictures today, it is really not, it is not 28 by 28. You will have 1024 by 1024. That's a normal size, okay? Let me shrink those ones a little bit so we can see it on one screen. Please take from today's session you know, broadening your way of thinking, you know. I will shrink it slightly so I will be able to, why it doesn't like me? Should like me. Yeah, I think it will be better now. Yeah, here we go. So I have a square basically. I have a square. This is my image, okay? You know, maybe even we'll make, no, that's fine. So if I have a white, I don't really remember, I always forget if white is 0 or 255. But let's say this point is a 0, it's a white cell. I write a 0. A 0, it means 5. It means white. So all of those could be white, you know? And if I look at the picture here, you know, all this side is all white. So all this area in a square like that, all the places that are totally white, they will get a 0 number. On the other hand, let's say this part, let's say my picture starts from here, okay? So on the very corner, those cells, okay, let's say how many we have here? 1, 2, 3. The first 3, okay, the first 3 on the right should really be 255. 255 mean black, totally black. Okay? Okay, and in fact, there are some more cells next to it which are also black. So all those blacks will be 255. So let's say 1, 2, 3, 4. The fifth one, it's gray. So let's make 5 numbers here to be 255. And then this one is gray. And the next one next to it, even the gray is even lighter. So let's say this one, since it's gray, it's not dark black, that will be, let's say 180, something in the middle. And the other one is lighter. So that's one, this cell supposed to be, let's say 70. I'm just making it up, meaning it is really closer to white than to black. And then the next one in the first row, it is really all 0, all the way to the beginning, okay? So that's like I filled the first row in the picture. And that's the way, I'm not gonna do the whole things, but that's the way really a computer keeps a black and white picture, okay? So all of those will be the first row, everything will be 0 here. And then I can continue more for the other rows. So each row in the picture, we translate them to 0 to 255 numbers, every cell. So we will have, if we have 28 cells by 28 cells, we will get a matrix just like this one of numbers between 0 to 255 in each cell. Is that clear, guys? How a picture is really kind of being taken in black and white?
Yeah.
Anybody? Just say yes.
Yes.
Good, thank you. Okay, now let's go and look at, okay, so I'm getting this image. So I want to show it to the computer. So far we have learned that we give to the computer a data set, if you recall from our other session. So if I go back to the Excel, I will get back to the Excel, and how do I take these metrics and turn it to one row? You know, I have 28 rows, yeah? And usually a database, we really want to put one row representing the number. So somebody had an idea and said, okay, no problem. Let's take the first row, copy it, put it here. Then take the second row, let me just fill it up so it will look like a row. And we know there is more black numbers here. So I'll write 255, 255, 255. And here I think it becomes to be more gray. So I will write here 170. I'm just making it up. And this one, let's say 80. And maybe this one also a little slightly gray, okay? So you take the second row, you copy it, and you put it next to the first row. So it start copying it to here, okay? So think about it. I take every row here and put it in one row. So I will have here a long row, which is a collections of all the rows. Now you can guess how many numbers will I have in this long row. It's the number of columns times the numbers of rows. That will be as long as this long line. So it will be 784. I think last session I said 684. I was wrong. It's 784. So I will have 784 numbers. And now think about it. I can get rid of all these images. And for me, from now on, the first image of 5, I will delete it. That was just to encourage the discussion. And I can say, you know, this long row represent the number 5. So all those ones, 784 columns represent the number 5. And here I will write the number, I will type the number 5 manually, meaning those 784 numbers represent the number 5. I can do the same things for another example from these data sets, okay? So I can move on and look at more numbers. Let's say the number 0. The number 0 will have other cells that they are 0. Some of them will be 255, the black one. The one that they are a little gray will get a little, you know, like a number between 255. But again, each number here, I can turn it into a long row. And what I'm ending up with, if I have 70,000, numbers, means I'm going to end up with 70,000 rows, and each row here represents a different number. So if number 0 will be represented by whatever those columns are, I will write a number 0 here, okay? And then all the other columns represent that one. By the way, I don't usually care about the name of the columns. All what I care is the sequence, and the sequence is important, okay? This one we usually call the target, because we're trying to predict which number this sequence presents. So what we usually do, we take the computer, we take the 70,000, and if you recall from chapter 2, we take from the 70,000, we take it and break it to 2 pieces. And that's something you really need to know also for the exam and also for your paper, as you're describing what I'm just saying now. You take the 70,000 in the example we have in the chapter, they take the 70,000 dividing it to 10,000 and 60,000. 60,000, we call it training data. And the 10,000, we call it the test data. If you recall, the reason we do that, we want to teach some algorithm how to identify numbers. What does it mean? If I give him a number 5 here, I give him the whole sequence. His job is to see the connections between all those columns and try to come and say, well, based on this sequence, this is probably 5. Second row, based on this sequence, this should be 0. And I give him a lot of numbers. I give him 60,000 rows. And he has to learn. How does he learn? We'll talk in a minute on different types of algorithm. I'm not going to make you know how those algorithm works. That's more advanced class. But I understand the idea. We're giving the computer all the sequences. We're telling them what the sequence is supposed to be. and he has to learn the meaning of the sequence relating to what the number I give him in the target column. So that one, we call it a Y, some people call it a target field, blah, blah, blah. Those ones are really the database or the columns that we will use, the data set to train the model. So we will have usually all those data on the right side, we mark it as an X, big X, because it's a matrix. And the column, the only one column, the first one, we always call it as a Y or a target, and that will be one long array. If I split the data to, I have 70 rows. I'm going to divide it to 60 rows. In the Excel, I will have 60 rows for the training and another 10,000 rows for the test, okay? That means I'm going to have two databases. So there is in Python, okay? In fact, all this data already prepared automatically for you. It's designed for learning. So if you go to the computer and just write, you can bring from Sklearn, Scikit-learn, a data set. It has a library of data sets, many of them, one of which is what is called MyNest, which is really these collections of data. And that one has two arrays. One is the right side that I mentioned before, all this data, and the other one represent this column. So here one more time, this one, the target, it's the column that tells me what is the actual number for every row. And each row in this array, you can tell this is two-dimensional array. It's like a matrix, like an Excel table. Each row, they didn't really put a lot of numbers, they put only the zeros, but here has to be other numbers that they are 255 or any number between 0 to 255, depend on which picture this one represents. So this database is already in Python. When you install Scikit-learn, when I gave you that library, the Scikit-learn has the data sets. You don't have to do anything. It's right there. You just give this command, you're getting really this special object. By the way, this is not a data frame. It is not NumPy. And if, God forbid, I give you a question in the exam, is MyNest is a data frame? You should say no. Is it a NumPy? It is not. It's a special object. And that special object, inside, it does have NumPy array for the data on describing the number, and it has another array, which is also NumPy array, which is showing the column of the target. Okay, that's describing how we get the data. Bottom line, I get the data. I want to know how many rows, how many columns. You see we have 784 columns. That's exactly what, that's the 28 by 28, 10 to 784. How many pictures do we have? 70,000. So the command shape, by the way, if you look here, when you write this command, MNIST, it's really like has two, it's really is like you can think about it as if close to a dictionary. It has two array of NumPy. One is for the X, one is for the Y, which is the target. That's the long row telling me what number they are. Therefore, if I take X and look at the shape, it tells me how many rows I have, meaning how many pictures, and how many columns describing that picture. When you look Y that shape, it's just telling you you have 70,000 numbers, but there is only one column. That's why the other one is empty. Okay, I really don't want to be technical today, but at least in the beginning so we can understand what's happening later on. One more thing there is, if you look at what this command means, that means in your matrix X that has all the images, please pick for me the row 36,000. You have 70,000 rows. If you want a specific row, you simply take X and put the number in. What you're really getting, this variable sum digit, this is really a row of 784 numbers. Sum digit, it's in fact one row representing a number, and it's representing it as 784. By the way, I mentioned it last time, and I said I won't kid you in the exam on that. There is a very special formula, a function, I should say, that takes whatever numbers here, turn them to a matrix. So if I have one long row of 784 numbers, I can convert them back to 28 by 28. In other words, instead of having one long list, I can get a matrix like that of 28 by 28 of numbers. It doesn't show me the numbers yet. It just tells me for in the black, you will put 255. Here, 255. So what this one does really takes one row out of this giant matrix and take that row of numbers, turning it to a matrix of 28 by 28. That's really what it does here. Then, you know, those people really have done beautiful job in Python. They tell you, you know what, you really want to see that picture? It's true you have only numbers, and those numbers mean nothing to you. If you really want to see it, just run this command. Plot, image show, just put the name of the, you know, name of that matrix, just put it here. Forget about the rest. I won't even go into that. Copy that, and you will see the image. Okay, so whoever really want to practice a little bit, I would strongly recommend try to do it yourself. But I don't really require. Okay, so this is just a way how you take one long row, convert it to a matrix, and from the matrix there's another function that actually will show you on the screen whatever it's that image handwritten number is. Okay, that's nice description of how that database looks like. Let's go. How do we say it in Hebrew? Tachlis. How do I use it? How that helped me to study? On how do I take those 70,000 rows and learn to predict which number is representing each row, and then do predictions on even handwritten numbers that I haven't seen before. So as we study in chapter 2, stage number 1, we take the 70,000 rows, we split them to the training and to test. In the training, we're going to have 60,000 rows, meaning 60,000 images, and we're going to have 10,000 images for the testing purposes. What does that mean? After we train the algorithm, I will introduce one of them, simple one in fact, and after he does the job, I want to see, can he also predict correctly on images he haven't seen before. That's our next objective. But before we get there, stage number 1, remember the X represent all the 70,000 rows. This is just a data frame, pandas data frame. The way you pull the first 60 rows, just simply telling him X represent all the rows, take it from the beginning, putting nothing here, then take it from the first row up to the row 60,000, not including the 60,000. That once will go to X train. And then we do the same things for the X test. That means start from the row 60,000 to the end, very simple. I'm not gonna ask you to remember all those by heart. If I give this question, I will write it very similar to the way I wrote it here, and by passively knowing, you will know exactly what the answer is. So I'm not gonna actively, like I could have asked, how would you write picking numbers from 10 to 15? and then it will be really a hard one because you have to write 10 to 16. And that's really not a fair question to a novice, okay? But if I write nothing to 60,000, you know, and I will say how many rows you're putting, you will know that you're putting 60,000 rows. That's a much easier to know. By the way, the Y is very similar, just the Y is one column. So the first one takes 60,000 numbers is a column, and the other one takes a column of 10,000. Okay, now that we have training data with the training Y, the target, we have a test data with the test target. Okay, what the next? What do we do next? Now, you know, we studied last time something called cross-validation. So what we're going to do in this stage, we're putting the 10,000 images aside, and we're focusing only on the 60,000 images. We're going to look at an algorithm that will help us to identify the link between every row to what number it represents, but we're going to do it in a smart way, similar to what we did in chapter 2. We're going to take those 60,000 and shuffle them around. And we shuffle them around so there's no really any sequence or whatever it is. And after we shuffle them around, okay, we basically, how do you really do it? It's pretty cool. I will not ask you to know the code, but to know the idea that you can shuffle numbers. So you take numbers up to 60,000, and there is a command in NumPy random library called permutation. It takes the 60,000 numbers and create a long column with numbers all over the places from 1 to 60,000. From 0, I should really say from 0 to 59,999. Okay, so I get an index, and then I can take that index, put it in the pandas array, and it will give me all the data shuffled down. I really don't need you to know, just think about it. I took the training data, next stage, we shuffle the data in the training data set. The training data set has all the columns, and one column represents the number. There is a way to shuffle all the images, okay? That's one. Second, we're going to start learning this topic step by step. Step number 1, we're going to be less ambitious in the sense, all our objective is not to identify every number, if it's a 0, if it is a 1, if it is a 5. We only want the algorithm to be able to tell me, if I show him a number, is it a 5 or it is not a 5? It doesn't have to tell me it's a 6. It's enough for me that it will tell me it is a 5 or other number but 5. That's a much simpler task. Everybody with me? Is that clear, guys? Hello? Just give me a sign of life.
Yeah.
Is that clear what our task is? So we're taking a very simple task. Our task is not to try to immediately know every number. We'll see it in the next section, in the next session, and we'll start maybe some today. But our objective first is to give him a lot of numbers, and the job of the machine learning algorithm is to identify if the number is 5 or not 5. So what do? I give that algorithm 60,000 examples. And there is a very interesting algorithm. Unfortunately, again, this is much, much beyond the level of this course, okay? But it's just good to know that it exists, and you definitely, without understanding how it works, and you really don't have to know, you can you can know how to use it to do the job. And that's called stochastic gradient descending. If you study mathematics, if you know what a gradient is, I just throw a word or two, but I definitely not going to ask you in the exam. It's not even written here in the book, but it's a good knowledge to know. Gradient, it's if you take any function and you take the first derivative with all the other variables. You will be shocked now if I tell you this algorithm, in fact, has a gradient of 784 as the numbers of columns. But you really don't need to care, okay? Just that general knowledge. Why is it called stochastic? Because it takes that for a different point in the database. But again, I just talked Chinese for a few seconds. You just need to know there is an algorithm called stochastic gradient descendants. And by the way, in real life, it's extremely used in many other applications. And I will mention it later on, probably next session, okay? Okay, so what that one does, by the way, Python already have made our life easy. They gave us a beautiful library called scikit-learn, and they are already built for us linear model. And in that linear models, they built a special object. We learn object-oriented. This is an object, and he is what is known as stochastic gradient descendants classifier, and he knows how to classify images or rows to two groups. That's I want you to know, okay? So the only things I need to do now is just like we're building up an object as we studied in Python, the first 3 sessions, I think, or 2, and then we build up an object. This one is a smart object that knows how to do the job. By the way, it has a number here. It says random states 42. Very common in machine learning. And why do we use it? It really has nothing to do per se for the algorithm. It just, this algorithm randomly picks specific some rows. So every time if you run it, you might get totally different results. To avoid it, you just give him a number there and you run your code with that number, so you always will give you the same results. Later on in real production, you might remove that number and then it will give you whatever it comes. But this is really number 4, just telling him every time I'm experimenting with this algorithm, please give me the same number, don't give me randomly picked, okay? But the real truth is working on randomly picking rows. He once pick it, he remember it, and then after he remember it, if you put the same number, it will give you the same result. That's just a comment, okay? So how does it work? I remind you in chapter 2, we said that all, in fact, almost all, I can say even all, the scikit-learn library, all their algorithms are written very similarly. After I create them, all of them has a function called fit. Fit means learn. In other words, please go look at all the rows in the data set, look at the target, okay? And try to learn. By the way, if you notice, this is why train 5, because I kind of skipped, I shouldn't probably. We converted the column that represent the target. If you see here, we had the X and we pulled, let me see where I saw it. We pulled, in fact, this one is the Y train. By the Y train is all the numbers. And you remember I said that we are trying to do, is it a number 5 or it is not a number 5? We're not trying to identify all the other numbers. So what we did, that's called binarizing the numbers. Meaning, if Y is 5, it is true. That's really what this line means. If Y train, I have a long column, go over the whole column. If you see, wherever you see the number 5, change it to say true. That's really what it does. If it's not number 5, say it is false. In other words, we're turning it to true, false variable. That's a little trick that we do in Python. We do the same for the test. If you recall, the test also has 10,000 rows for the train. The test has for the train, sorry, this is the X, and has also 10,000 numbers for the Y. So we turn the Y also to true, false. So basically what we have many rows and one column that has true, false. And that's what we're feeding into the algorithm. So basically the feed command, I might ask a question. I give that line in the exam and I will ask what this line do. And your answer should be as it's in all other scikit-learn library, this one train the algorithm. That means the stochastic gradient descendant classifier is being trained. How does it do it? It's really beyond the scope of this course. But at least you know that when you use an algorithm, and I told you it's an excellent one to identify yes, no, true, false type of. So if the Y train 5 is true, false, this is a beautiful algorithm that know how to learn the connections between all the 784 numbers in every row to if it is true or no. Okay, that's what this line does. Then we go on, and then we tell him, listen, can you predict for me now that you learn from those 60,000 rows? Let's see if you can identify a specific row. Can you predict what the specific row represents? Which number? By the way, if you look some digit, it's done here above. Kind of skipped. I didn't want it to be technical today. If you see a sum digit image, it is row number 36,000. So this is the digit, okay? And this is really the one that I'm asking him, can you please tell me, can you tell what, if it's a 5 or not? Okay, we know it is a 5 because we just printed it, yeah? So let's see if he can tell me if it is a 5 or not a 5. Is that clear? I'm not trying to say, tell me which number it is. He has only to tell me, is it a 5 or no? So I trained him, and after I trained him, I asked him to predict. And his predictions, I would like it to say true because I know that specific image is a 5. And he did. In fact, he told me, he gave me it as a way of an array. He told me true. True means this number is 5. Questions, guys, before I move on? That's a hell of a lot of material in one breath of speaking. Anybody, guys? Anybody?
No.
Are you sure? Can I ask a question? Let's see if anybody got it. Can I ask? Don't be shy, guys. It's not easy stuff. Honestly, it's not. Okay? So if you have a question, please feel free. Okay, I will move on. Let me ask a question. What should be the command? Here, in fact, I will show it to you here. Okay? I want to know if a row in the line 20,000, if it's a 5 or no. What should I do? And we do together. What I should do here in this line, anybody? I want the image in the row 20,000. How should I change this line? Anybody? The way it is written now, which row does it give me? Is that row number 36,000?
Yeah.
Yeah, that's why we wrote row number 36,000. X is like a huge matrix, huge, and I put which row it is, it will bring it that specific row. So if I want row number 20,000, I will just write here row number 20,000. So some digit will really represent that specific row. By the way, if I follow the whole thing, it will print whatever number it is, okay? You know, will convert row number 20,000 to an image of 28 by 28, blah, 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 blah. Bingo, give me. What would be really nice, what we as a programmers do, we just write a little nice function, print an image, and then we just transfer to it a number, you plug the number here, blah, 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 and boom, show me 5. That's usually what real people do in real life. You don't really repeat the whole things again. Okay, so if I want row number 20,000, that's my command. Okay, next, I want the algorithm, after I trained him, okay, I want him to predict if it is which number it is. So which line here give me the prediction? Anybody? See, some digit is the row. Is that right? It's the row itself, correct? Hello?
Yeah.
So what does it really do? In fact, just remember, what is really the SGD? I just called it that name, but it has a function called predict. 2 functions you must know. Teach the algorithm. Predict what this is supposed to be. That's your job algorithm. You need to do 2 things. 1, learn from what I gave you, and I gave you a hell of a lot of data. Second, when I give you a row, you should tell me what do you think. And how do you tell me how you think? You predict. And you tell me, if I put 20,000, it could have tell me true. If it's true, that means it's a number 5. And if it tells me false, it is not a number 5. Very simple. Everybody got the objective, what an algorithm is supposed to do? 2 things. 1, to learn. And how does it learn? Using the feed command. What do I give him to learn? The training data set. The training data set has all the columns and 1 column, which we call him the target. Okay? After he learned, his job, when I give him one row very similar to all the rows in the training, he should be able to predict. And in this case, he has to predict if it is a 5 or not a 5. So far, so good? Everybody happy? By the way, the exam will be in this style. Okay, I will lead you, I will help you, but the basic understanding on the process, I think it's extremely important. I will try not to be technical at all, as much as less, really. Okay, good. Now, I gave you 1 example. I took 1 row, 2 rows, 3 rows, but really, how do I measure if this algorithm is a good one? A good algorithm will be good if every row I give him, he will be able to predict exactly what it represents, doesn't it? Do you guys agree? Anybody? If I tell you this algorithm, okay, 90% of the time he is right. Will you be happy with that result or no?
No, it's not enough.
Who said no? What's your name? One more time.
Ruben,
Ruben. Yeah, I agree with you. Why?
I think with algorithm we can be more precise.
Yeah. Why did I choose 90? I didn't choose 90 coincidentally. You know what? Let's make it 80, and I will help you. If it will predict 80% correctly, I would be very disappointed because I could have done a better job without an algorithm.
Like you said, 90, it's huge, like it's less on the side 10. It's a huge number. I think it needs to be like 91, 1 something, not less.
Think about it. How many digits do we have? 0 to 9. Is that right?
Yeah.
So total, we have 10 digits. What is the job of this algorithm, by the way?
Alors, je retrouve dans un autre tube.
This algorithm has to do very simple job, only to tell me if it is a 5 or not. So how many digits between 0 to 9 I have? Only one. Is that right? So if somebody shows me all the images and I say none of them is 5, how much wrong I can be? Everybody got my question?
No, it's a new question.
I repeat it. See, you know that there are numbers only between 0 to 9. You agree?
Yes.
And I tell you, I want you to guess. I show you the card that has numbers, but I show you the back. And I tell you, can you guess? Is it a 5 or not? If you always say no, all the time you will say no. How many times you will guess correctly? 90% of the time, isn't it?
Yeah.
Because 90% of the time, the numbers is not 5. So I don't even have to look at the card. I will be correct 90% of the time.
Yes, for sure.
Does that make sense? So in a question like the one we analyze now, getting a prediction of 90% sound wow. This is great.
Yeah.
But
It's not enough because we don't need algorithm to find 90%.
Okay, but getting 90%, it's really like guessing every time that it's not a 5, I would guess also 90%. So what a big deal on this algorithm. So as we see in a minute, when you run this algorithm using cross-validation, what does it mean cross-validation? I will remind you from chapter 2. That means I take all the records, all the images. I will speak, here we use they use here in the chapter, cross-validation with 3. You don't really need to do that because you don't really need to go over that. That's if you really want to learn some programming. But the Scikit has a nice function that does the job automatically. What it does, I can give him this function, cross-validation score. I give him the data, I give him the algorithm, that's the algorithm, and then I tell him what is the target, and then I tell him do cross-validation on 3 faults. What does it mean? Take the data, take 1/3, put it aside. 2/3, study the relationship with the target, between the rows to the target. Then try to estimate the other 1/3 you put aside. Do it 1 time, see how many times you are correct, put it aside. Do it a 2nd time. Take another 1/3 and the other 2/3. Teach the algorithm with the other 2/3. Try to estimate the remaining 1/3. See how many times you are correct. And do for the last 1/3. So you do it 3 times. When you have cross-validation 3, you're really dividing the data to 3 pieces. 1 piece and 2 pieces to learn, and then you estimate the other 1/3. If the cross-validation will be 10, that means you divide the data to 10 pieces. You take 9 pieces to learn and estimate the 10th one. And then see how many times you are correct. Here, he automatically does the whole work. This is the beautiful about studying a little bit Python, because someone can write it manually. This does exactly what this one does, but this is an elegant one line. And it tells me if you do it 3 times, on the first one, you got 95% accuracy, 96 accuracy, 96 accuracy. First of all, the fact that it's above 90, I can tell the algorithm does okay. Is that right? At least it's not like a stupid one that says everyone is not 5. At least it's better than that. But is it a really good one? I doubt. You know, he's doing okay, but I wish to see here really close even to 99, because after all, that's why I'm using algorithm, not to be slightly better than a dumb person that know nothing, that can say everything is not 5, okay? So far, so good. So that's one. By the way, there is another example that showing how you can build a DAM, like the example I gave. You can build your own algorithm. This is, again, not going to ask you, just know that you can build up your own algorithm that can work like the stochastic descendant gradient. So Python gives you all the tools to write your own. This is like somebody wrote a stupid algorithm that all what it says, everything that you show me, I will tell you it is not 5. And no surprise, the prediction is around 90%, which makes sense when you're just guessing nothing. You're not really guessing anything. You just say everything is not 5, okay? So how do we really measure if its algorithm is a good one or is it a bad one? That's the next topic. We learn now that we try to do prediction, and we want to know if the algorithm that somebody has sold us, by the way, a lot of people go and buy those algorithms. They don't write them themselves. Many times, maybe Python doesn't have algorithms that they wish, or they want to modify it, they just go and buy it. After you buy it, and you say, okay, how good it is. So we use something called confusion matrix. What does it really mean? How do we really want to test our own algorithm? And here is what the meaning of confusion. I won't get into the technical. You can run this command with cross validation predictions. You get the results, and then you get the predictions. You use the prediction, and there is a command called confusion matrix. What does it do? Very, very, very important. Okay? On one hand, it shows you, okay, the columns showing you how many in reality there are not 5, and the other column in reality how many there are 5. On the rows, it shows you how many you guessed as 5, and how many you guessed not 5, and how many you guessed 5. One more time, and then you will tell me what you think. See, this matrix, let's make it in Excel, it will look maybe better. I'll make it bigger here. Basically, this is the true not 5. That's that column. And then I have a column, it is 5. Okay? In real life. Remember we had 60,000 in the training data set. Remember that? Now, when I made my guess, this is what I predict. That's what my algorithm predict. That's algo predict. Okay? If I write here, for example, out of the 60,000, there were here, I'm just making it up. In a minute, we'll look at the numbers. Let's say I get a number here. I write this one, 55,000. And here, 0. Here is 0. And here is 15,000. Let's try to understand the meaning of this data. This is the algo predict. I should write the algo predict not 5. And here we'll write algo predict 5. Fair enough? So what does it really mean? In real life, there are 55 numbers, okay, that they are not 5. Fair enough? And the algorithm was able to predict all of them. So this is perfect prediction, isn't it? It never made any error. Whenever was 5, it did not say it is not 5. So the fact that I have here 55,000 and here it's 0, it means the algorithm always predicted any number that is not 5, it always said it is not 5. Also, what the meaning of this 15? In the data set that we have, there are 15,000 numbers that there are 5. And the algorithm, again, was perfectly predicting that those are really 5. So this is a perfect algorithm that give me these results that I have numbers in the diagonal, meaning if it is a 5, it predicts it is a 5. If it is not a 5, it predicts it is not a 5. That's a perfect prediction. Everybody got the idea? Anybody? Hello?
Could you repeat the question, sorry?
Yeah. So I'm trying to explain what a confusion matrix does. You know, we had in the training data 60,000. By the way, this should be 5,000. I apologize. My mistake. That should be 5,000. The total should be 60,000. I have 60,000 numbers. Fair enough? I give it to the algorithm and I ask him, can you please predict 11 the data, blah, blah, blah. And he made the predictions. I looked at his predictions. I look at what really it is. And I notice that every time the number is not 5, the algorithm say it is not 5. So he was right, correct?
Yeah.
Yes.
Yeah. So every time I showed him a number that wasn't 5, he really said it is not 5. I showed it to him 55,000. And every time he was right. So that's really the meaning of 55,000 in this square. Again, I showed him also numbers of 5. I showed him 5,000 of 5. Every time I show him the number 5, he said it is a 5. So again, he predicted perfectly, correct?
Yeah.
So if I see a confusion matrix that I have numbers in the diagonal, that means those are the numbers that it predicted perfectly.
If you show 555, what will be the result?
It just, you know, in the numbers in my database, I had 60,000. Remember, we took them randomly out of the 70,000. I just made it up that those 60,000 had only 5,000 to be 5, and 55,000 are like 0, 9, 8, all other numbers. So in every time...
The number is 555. Like the algorithm predict 5 or not 5?
That's 55,000 numbers. They are not 5, and 5,000 numbers, they are 5. And every time I showed him the number 5, he was able to predict that it's a 5.
So Amos, does that mean that if in column E 10, if for example it predicted it was a 5, let's say there is like 10%, so 50, he said that 500 in this 5,000 there were 500 that it say was 5, but it was not. So it should have been like a not true enough, and then also predict there.
Close enough, yeah. See, I have 60,000. You know, if you think about it, I have 60,000 numbers, and 55,000 of them are not 5. All the other numbers. And 5,000 is 5.
J'ai peur, mais je crois que j'ai pas d'argent.
C'est relié à ta carte normalement.
Yeah, I
Pas
just, how
de-
do I,
Ruben, t'es en...
Paris convert.
yeah, I forgot how
Sure.
to,
Codar.
audio, nope, oh yeah, here. That's okay, that's fine. Okay, so what, maybe I will take one step and that will be clearer. Okay, what does it really mean if I write here the number 2 and I write the number 4998? Okay, and here I will write 54998. What does that mean? Pay attention. This time I showed the guy, 55,000 numbers, okay? And see what he did. I showed him 55,000 numbers, okay? And what his guess, okay? And I showed him, in fact, sorry, I showed him 60,000 numbers, but he kind of made a mistake. What is the mistake? Okay, I should really put a 2 here as well. My mistake. No, that's 2. Yeah, I should put a 2 here. Okay. Okay. I showed him 55,000 numbers of 5, and he was able to say correctly that there are, sorry, I showed him 55,000 numbers that they are not 5. He was able to predict correctly 54,998 times correctly, and only 2 times he made a mistake. He said it is a 5, but really it's not a 5. So this number tells me how many times he's right when I'm showing him number that is not 5, and this one shows me how many times he is wrong when I'm showing him a number which is not 5, and he thought that it is 5. Okay?
Perfect.
In addition, here, I showed him 5,000 numbers that they are actually 5, but he was right, and he said out of the 5,000, 4998, it was absolutely correct. It said it's 5, but he made a mistake of 2. Okay? So what do we really learn? The higher the numbers in the diagonal, it means the predictor predict well. The numbers in the other diagonal, the higher they are, that means this algorithm doesn't do a good job. Does that make sense, guys?
Yeah, definitely.
Yes.
Okay, good. So if I was just really even, let's emphasize that. Let's say now, this is 30,000. And here, I will put 20,000. What does it really mean? I showed him 50,000 numbers of 5. He was right only on 30, and he was wrong on 20,000. So as big as this number is, it means he's doing a bad job. Some things here, let's say here I will write 1,500, and here I will write 3,500. It's still 5,000, is that right? Out of the 5,000, he kind of correctly predicted 3,500 he predicted correctly, and 1,500 he predicted incorrectly. So the confusion matrix is a really good first step to see how good is the predictor. As the numbers in the diagonal are high, that means it's a good predictor. As those numbers are bigger, that means it's a bad predictor. Is that clear, guys? That makes sense?
Yeah.
Excellent. So now, just for terminology, okay, as terminology, we will talk about what is called true positive, true negative, false positive, and what does that really mean, okay? Let's look at the Excel again, okay? Make it like that so we can see the whole screen. Okay. If we look at this screen, how do we call these 30,000 in this example? We want to give it a name. This 30,000, it predicted correctly. That's why we call it true positive. It's positively made the right decision. So if it's not 5 and he said it is not 5, it's true, it is not 5, that means it's a true positive. It's positively said that it's not a 5. Therefore, we call that. It's really depend on the terminology, how we define true and false. Here we define the true to be if it is not a 5. Since not a 5 is the true, so we said true positive, we have 30,000 cases. Okay, just really a definition. Okay. On the other hand, this number, it is a true negative. It is not a 5. It is a 5. I mean, it's not a 5. It's really kind of confusing in the example in the book. Okay. So this one, it's a true positive, and this one, it's a true negative. That means it is a 5. It is not a 5. Okay. If you look at the example in the book, this is the way the matrix looks like. I will increase the size of it. That's always happened to me. Okay. And this is a perfect prediction. This is less perfect because we have number in the diagonal and we have some other numbers on the side. Those are errors, in fact. The predictor did not predict correctly. There's only one simple command, confusion matrix. What do I need to give this function? Very simple. I give it the true numbers. You know, that's the long column. True, false, true, false. If it is not a 5, it's true. If it is a 5, it's false. And then I see what they predicted. And if it's the same, you will put it in one of those diagonal. If they are different, it will be in the other side. So those are error, meaning that whenever this column doesn't match the other column, meaning the rows are not matching, it will be in the other side. When those matching, it will be or here or here. If both of them will say true, it will be here. If both of them will say false, it will be here. Okay? And that's really what it means, true positive, false positive. Okay? We'll get more. Go ahead.
How do you, when you train a machine like this, how do you train it? Meaning, like, do you have to also have like so if you train it only with a machine, how could he check his answer? So you have to check it also yourself, correct?
The truth of the matter, the machine,
with the human eye.
as I said, this is the beautiful. We took images, we converted them to a long row. Say to machine, take those 60,000 rows. And I tell you, every row, what they represent. Learn it. How does it learn? I don't care. Somebody gave me an algorithm. In this case, we got an algorithm called stochastic descendant algorithm, okay? So he learned. Now I tell him, here is another database. Try to tell me, can you predict, based on the rows I give you, can you predict what they represent? So he's making a prediction. I take the prediction and I compare it to what really those rows represent. And that's what we do in the confusion matrix. I compare the prediction to whatever it really each row represents. This is each one of those is a column of numbers, and this is a column of one column of numbers. So he's comparing those two and trying to see, are they matching? If they match and both of them are true, he put them here. He found 54,579 actually predicted true was really true. He found 5,421 cases that when he said it is not 5, meaning it is a 5, it becomes to be a 5. So he was right. He always was right. And if you add those numbers, you get 60,000. He never made a mistake. That's why it's a 0 and 0. On the other hand, here, he made some errors. When actually it was a 5, he predicted it to be non-5. The same things on the other one. This one represents making the other type of error.
And I heard also, Amos, that you know, like the software that they use to do to verify if you're not a robot. I forgot how we call it, but basically, you know how they ask you to feel what are the numbers you can see. You know, they give you an image and they ask you what are the numbers you can see.
Well, that will be the next section.
Oh, okay.
And we will talk about not only is it a 5 or not, I want you to tell me what number it is. So then that becomes to be a little more complicated because here I'm asking him to identify 10 different digits, not just if it's 5 or not 5.
Mm-hmm.
And that will be the next part. But at first, we try to find how do I measure if an algorithm is good or not. And that's why we use the confusion matrix. Stage number 1, we can see in our eyes. If this is like this is a perfect algorithm. If it is not, then it's not perfect. And then we try to see, so how do I translate that? Is that still good or is it bad? And then we get into what is known as precision. So we take true positive, that means we take this number, and we take false positive. False positive means I said it's positive, but it really isn't. This is like the 1300 here, or 7. I said it's a positive, but it really wasn't a positive. So that's all the times that I said positive. All those cases I said, this is a positive action, or positive whatever. In this case, this is a 5 or not a 5. But I was wrong in 1300 or 7. So if I take how many times I was right, in this case was 53 to 72, divided by this number plus how many times I was wrong. This number should be between 0 and 1. If I perfectly, correctly identify true positive, this will be 0. Is that right? The false positive will be 0. This is known as a false positive. That will be 0. So that will be the number divided by himself. It will be 1. So if I'm making a mistake, the more mistake I will make, okay, this number will be higher and that ratio will go down. So precision is kind of telling me how many times that I said this is really a true, I was wrong. And that precision. Fair enough? So if I was able to predict correctly what I thought it is positive, then it is a precision. Everybody got it? That's a little confusing. Please. Our session going to be ending by 6-7 minutes, but I'm going to go another concept. They are so easy, but honestly, they for some reason have that characteristic to confuse you big time. And for next session, which I want to go over, recall versus precision, and I really want to show those charts. I don't want you to get lost. When I get to here, and I will get here, I don't want you to get lost because it's really easy to get confusing. Honestly, it is for some reason, I don't know why, but it does. So just repetition. There is nothing better than repetition to learn what precision is. One more time, precision is how many times when I said positive, it was positive. How do we define positive? It's a different question we said before. But if it is, I said it's positive, and actually it was a positive, out of which I said. How many times I said positive, it's the denominator. How many times I was right, it's the numerator. So this number is always will be lower than 1. There's another concept. So that could be a good measure for how good is the algorithm. Somebody said, you know what, I have another idea. Let's say how many true positive you have, the same things, the true positive, let's look at the Excel. This is this number, but don't look, okay, how many times you were right looking at the rows. This is how many times I said a positive. I said 30 plus 15. So 30 divided by 45, that will be my precision. But why don't you try looking at it in a different direction, okay? You say, how many times you were right out of all the cases that in real life, they are positive. Positive in the, it means it's not 5. So in real life, there are 50,000 cases that are not 5. You were wrong 20,000 times. So how many times you were right? It's 30 divided by 50. So in recall, we measure it, how many times I was right out of how many positive cases there are. And in precision, we measure how many times I was right from the times I'm said there are positive results. It's a little confusing. Just this might help you a little bit. When we look this way, this is precision. When we look this way, this is recall. Now, by the way, there are many cases in which precision might be high and recall might be low, okay? And just as another way to try to understand that one, all the numbers in here, they are true, negative, okay? Here, it's really the definition the other way around. Negative in the sense that it's not 5. But basically, those one, it's really the higher they are, the better is the algorithm. This one, the higher they are, the negative, the less. I might mix up the concept because the way how you define negative and positive, but it really depends on the way you yourself. I usually like to, positive for me, it's here, positive for me, it's here, negative, it's here, negative, it's here. But you can turn them around, it doesn't make a difference for the definition. Okay, let's move on by saying you don't really have to work too hard. You know, the computer already have a function. You give him the data, okay? And he automatically will find the precision, it will find the recall. You see, you have a recall function and you have a precision function. What do you need to give it? And that we will cover more next session. I will just start today. I only have to, I will run it to the confusion matrix, and then I run to get the score. And there is a function called score. After I get the score, the precision score and the recall score, I will try to play with it. Which one do I want it to be better? Some algorithms, you know, what is our objective many times? We get a lot of algorithms. Which algorithm should I pick? The one that have a higher precision or the one that has a higher recall? And the answer is really depends on what is your objective. And this following a paragraph gives you a nice example. I won't get into that. I will mention it next time. I will just say that some people try to find a general criteria called F1. I'm not going to ask you to remember it, although it should be kind of easy. TP and TP is here. It's the same thing that it exists in two formulas. What you do in the F1, you just take the average of those two. I won't make you to remember it. If I ask a question on that on the exam, I definitely will give you the formula, okay? Basically, F1 is kind of a measure that kind of combine recall and precision to make a decision which algorithm is better than the other. And some people will pick one that has a higher F1. But it's not really always the case, depend on your cases. Sometimes it's good to be right all the time. Let's say, God forbid, you take a test if you have a cancer, okay? You really want that test. If it tells you have a cancer, you want to be sure you do have a cancer, because you'll be really disappointed if they tell you you have a cancer when you do not have a cancer. So that's really painful to work when you get out of the lab and somebody told you you have a cancer. You know, you rather, you know, or that's one way to look at it. Someone else will say, you know what, I rather that the algorithm will be wrong, even if I don't have a cancer, to tell me that I have a cancer, okay? As long as that when I do have a cancer, you always will be right. So it's a trade-off. So one algorithm, okay, if you have a cancer, it will always be right. That might be a good one, because that means it has a high recall. It has a high recall. Whenever you have a cancer, it always will tell you you have a cancer. On the other hand, the precision might not be right. It might tell a lot of people that they have a cancer when they don't have, okay? And that's really depends on the preferences of the people. Many people might prefer to be sure if they have a cancer, the algorithm will tell them so they can take care of it. And they won't get too upset if you told them they don't have and they do have, you know? If you will tell them they have and actually they don't, because then that will be really a bad scenario. Anyway, I see that I lost a lot of you guys. I hope it wasn't too boring. By the way, this is real machine learning study. I try to avoid the technical aspect. Please read the chapter. Okay, I want to finish this chapter next week and tell you exactly, I will write the assignment for next week. And next week we'll finish the assignment, and then last session we talk about the exam. Thank you guys. Thank you, Moria.
Thank you, Amos.
Thank you guys. Please do watch the videos. Don't wait the last minutes. You're going to have a lot of exams.